Now we are at the lecture 12. What we had discussed till now was how to do the element calculations in the master element. So we had transformed our equations from the physical domain to the master domain. And in the master domain, we had said that we will be defining the shape functions for the element and transform the integrals that we had over this domain. Okay, the question was now how to convert these integrals into a computer implementable form, because for us to do the integration of polynomials and other functions by hand is easy, but how will the computer do it? So computer generally, what does it do? It integrates some quantity by replacing it with a sum. So sum over some points 1 to n bar, let's say. So sum of the function psi, the f at the point psi I into so called weights wi. These points psi I are called integration points. And wi is the corresponding weight. So now the question is that fine, how do we choose points psi I and the corresponding weights wi. So what do we use here is the so called Gauss-Legendre integration rule. What is the basic idea? I have now my master element spanning from psi equal to -1 to psi equal to +1. The center of it is the point psi equal to 0. So what I am going to do is I am going to choose points which are symmetrically placed on either side of 0. So I can choose this point and the corresponding point here. Okay. These are going to be our choices of integration points, such that if I call this point as psi 1, this point as psi 2, this is psi 3, psi 4, then psi 1 is equal to minus psi 4, psi 2 is equal to minus psi 3. Further, for this set of symmetrically located points, we will have the same weights. So W1 will be equal to W4 in the example that we have taken, and W2 will be equal to W3. So we will say that the feature of this method is 1, the integration points are symmetrically located on either side of 0. And the weights for a pair of such symmetric points is the same. Now, how do you design the location and the weights of the points? So, the basic idea again is that we would like our choice of these points and weights to be such that for a polynomial of a particular order, the integral comes out to be exact. So, if my integrand here is a polynomial, if this guy is a polynomial, then for a particular order of the polynomial, this integral should be exact, that is, the sum should be exact, f psi I wi. Okay. Now, let us go ahead and construct these sets of points. Let us take the first example. First example is, let us take n equal to 1. If I take n equal to 1, then I notice that the point psi 1 can be nowhere else but at the 0 location, because it is a symmetrically placed point, and the weight will be, corresponding weight will be W1. Okay. Now, W1 is equal to what? That is what we have to determine. So, let us take first a constant. I integrate the constant from minus 1 to 1. So, let us take the constant 1. This integral will be equal to 2. Now, this I would expect the one point rule to at least integrate the constants correctly. So, it is going to give me from this one point rule f at 0 into W1, which is equal to 1 into W1. So, implies W1 is equal to 2. So, this is going to be our one point rule. So, one point rule for n equal to 1 is implies I have the following pair, the point is 0 and the weight is 2. Okay. Now, for which higher polynomial does this one point rule do an exact job? So, let us look at the next higher polynomial. Let us see. If I take f psi to be a linear in psi, so it is a naught plus a1 psi d psi. So, if I do this integral, so I am going to call this integral as I1 is equal to this. This integral will turn out to be 2a naught. The second part will drop off, because if you see this, a1 psi is an odd function and the integral of an odd function over this interval is going to be 0. Okay. Now, this, my question is it equal to what I get out of the one point rule? So, out of the one point rule, f at the point psi equal to 0 is a naught into the weight at the point psi equal to 1, which is 2. So, this integral is exact. So, the one point rule not only integrates the constants exactly, it also integrates the linears exactly. Let us become a little bit more greedy and ask whether this integral can also be obtained exactly using the one point rule. So, this integral, if you see, will be equal to, by what we have done, 2a naught plus this part will drop off. This part is now again an even part, so it will give me a value which is equal to 2 by 3 a2. Okay. Now, if I look at the 1 point rule, so the 1 point rule gives what? 1 point rule will give me this integral equal to f at 0 into w1, which is equal to a0 into 2, which is not equal to I2. So, the 1 point rule is only exact for all polynomials which are linear. For higher polynomials, it is not exact and it will not give you the exact value of the integral. So, for this, now let us go to the next step. So, we go to the 2 point rule. If I take the 2 point rule, what do I know? The points are psi 1 and minus psi 1, and the weight, corresponding weight for the two pair, because these are symmetric points, so both will have the same weight. Okay. So, this is my point, if I want to call it psi 2, okay, is equal to minus psi 1, and the weight of W1 is equal to W2. Okay. So, what we want this 2 point rule to be at least exact for the quadratic, because the 1 point rule could not do it. So, I expect the 2 point rule to do it. So, let us take I2, which we got as 2a naught plus 2/3 a2. This will be the functional the integrand evaluated at psi 1 plus the integrand evaluated at minus psi 1 into weight 1. Now, this is equal to, this is f at psi 1 plus f at minus psi 1 will be equal to, if you work it out, 2a naught plus 2 a2 psi 1 squared. Okay. So, now if we compare the two, the coefficients of a naught and a2, I get as this whole thing into W1. If I compare the coefficients, then I will get 2W1 is equal to 2, and if I look at the second part, it will be 2 psi 1 squared is equal to 2 by 3. So, 2 psi 1 squared is equal to 2 by 3, sorry, 2 psi 1 squared W1. From here, W1 is equal to 1, and from here, by substituting everything, I get psi 1 is equal to plus minus root of 1 by 3. So, choosing these points, psi 1 equal to plus minus root of 1 by 3 and W1 is equal to 1, the summation for the 2 point rule gives us an exact integral for I2. So, our 2 point rule n equal to 2 will be equivalent to saying I have the point psi 1 equal to minus 1 by root 3 and the weight W1 is equal to 1 and the point psi 2 is equal to 1 by root 3 and the weight W2 is equal to 1. Okay. Now, let us see whether this 2 point rule can give us an exact integral for a cubic polynomial. So, what will the cubic be? This integral, if I do, it will come out to be exactly the same as the integral I2. or it will be given as 2a naught plus 2 by 3 a2 and we will see by taking the 2-point rule I will get the exact integral for n equal to 2. Okay. Now let us get greedier. Let us ask if it will do the same job for I4, which is the integral of a fourth order polynomial. So it is a naught plus a1 psi plus a2 psi squared plus a3 psi cubed plus a4 psi to the power 4 d psi. So if I do this integral, it will turn out to be 2a naught plus 2 by 3 a2 plus 2 by 5 a4. And if I do the 2-point integration rule, it will give me, the 2-point integration rule will give me 2a naught plus 2/3 a2. This one should check, and this is not equal to I4. Okay. So the 2-point integration rule can give us an exact integral for all polynomials up to a cubic. Okay. But for a fourth order, it does not do the job. So then we naturally go to the 3-point rule. So if I take a 3-point rule, what will be the points? I will have psi 1, psi 2 is equal to 0, psi 3 is equal to minus psi 1, and here weight 1, here I will have weight 2, weight 3 is equal to weight 1. So if I look at this, here is my psi equal to 0, this is my psi 2, this is my psi 1, and this is my psi 3 equal to minus psi 1. Okay. So if I take this and say that okay, it should give us an exact integral for the fourth order one. So I4 was equal to 2a naught plus 2/3 a2 plus 2/5 a4. What I want from the summation is equal to f at psi 1 into W1 plus f at psi 2 into W2 plus f at psi 3 into W3. Now this will be equal to W1 into f at psi 1 plus f at minus psi 1 plus W2 into f at 0. Okay. Now f at psi 1 plus f at minus psi 1, you see that this is also a symmetric quantity. So this will be equal to 2a naught plus 2a2 psi 1 squared plus 2a4 psi 1 to the power of 4. Okay. This guy will be 2a naught. So now if I match the coefficients of A0, A2 and A4, we see that by matching the coefficients of sorry, this won't be, it won't be equal to 2A0, F0 will be equal to simply A0, okay, by what we have done. So by match, if I match the coefficients, I will get 2 W1 plus W2 is equal to 2. This is my first relationship that comes out. Then coefficient of A2, I will get 2/3 is equal to 2 psi1 squared W1. Coefficient of A4 will give me 2/5 is equal to 2 psi1 to the power of 4 W1. Okay. So if I take the ratio of these two things, this will give me psi1 squared. So divide this by this is equal to, so what will I get? Psi1 squared is equal to 3 by 5, implies psi1 is equal to plus minus root of 3 by 5. So see, it's very easy to get these integration point locations, though as the number of points increases, the task becomes more and more laborious. Okay. So if I have that, so now substituting this expression for psi1 squared from our previous equation, you will get that 2 into psi1 squared W1 is equal to 2 by 3. So 2 psi1 squared into W1 is equal to 2 by 3. So implies W1 is equal to 5 by 9. Implies by our first equation, since 2W1 plus W2 is equal to 2, implies W2 is equal to 8 by 9. So we have found the locations of the points and the weights. So psi1 is equal to minus root of 3 by 5, W1 is equal to 5 by 9, psi2 is equal to 0, W2 is equal to 8 by 9, psi3 is equal to plus root of 3 by 5, W3 is equal to 5 by 9. This is 3-point integration rule. It turns out that if I go and check now for the fifth order polynomial, so this was derived using the fourth order polynomial. If I find I5, which will be the fifth order polynomial, for this also the 3-point rule is exact. So if I write it down, the rule, the order of the rule, and the polynomial order p bar for which it is an exact. So the 1-point rule was exact for the linear. The 2-point rule was exact for all polynomials which were at most cubic. The 3-point rule is exact for all polynomials which are at most fifth order. this way we can continue. So, can we come up with a generic rule? So, a generic rule, yes, we can come up. You see that if I have n, if I have a polynomial which is 2n minus 1 p bar equal to 2n minus 1, then the endpoint rule does an exact job. So, if p bar is less than equal to 2n minus 1, then endpoint rule is exact. Okay. So, if out of this, how do I choose the appropriate integration rule? So, it is very easy now that you say that if I have a polynomial of order p, then n should be greater than equal to p of p bar, order p bar, p plus 1 by 2. So, if I use an integration rule with number of points greater than equal to p bar plus 1 by 2, then I know this integration rule is going to give us an exact integral for that particular polynomial. Okay. Now, let us say that if p bar is odd, then n turns out to be p bar plus 1 by 2. So, n is equal to p bar plus 1 by 2 will do the job. So, I am going to fix my polynomial the integration rule to n equal to p bar plus 1 by 2. If p bar is even, that is the order of the integrand is an even, then I would choose n equal to p bar plus 2 by 2. So, that is go to the next higher polynomial integer point. Okay. So, with this choice of this integration points, I can expect that whatever integrals I have to do, if they are polynomials, I will get an exact value of the integral, and this is very important from our numerical computation point of view. Question is, can we construct these integration points easily through some other means? It turns out that yes, these points psi I are the roots of Legendre polynomials defined in the interval minus 1 to plus 1. So, here we have an example of the Legendre polynomials that can be used to obtain the locations of the integration points. For example, if you look at this first polynomial, okay, it has its root nowhere, okay, in this interval from minus 1 to 1. Second one has a root at the point x equal to 0, which for us is the point psi equal to 0. Okay. So, this is nothing but the point for the one point rule. If you look at the third one, the second polynomial, which is a quadratic polynomial, you see that the roots of this appear at x equal to plus minus 1 by root 3. Okay. So, these are nothing but again our the points, the coordinates of the integration points for the 2-point rule. You look at the third one, here it can be written as half into x into 5x squared minus 3. So, the roots are x equal to 0 and x equal to plus minus root of 3 by 5. So, this is exactly what we had derived using the long approach. Okay. So, once I have these points, then I can go back to what we had done there and obtain the weights for the polynomials for the integration rule. So, I can go on with these Legendre polynomials and I can get the integration rules, the location of the points corresponding to the integration rule of choice, and it is given here in the form of a nice table. You see that if I have the 1 point rule, there was nothing big that had to be done. The location is psi equal to 0 and the weight is 2. If I have the 2 point rule, here I have 2 points with plus minus xi as my coordinates. So, this is the symmetric points and the weights are this. And you see that here effort has been made, this has been borrowed from a book, to obtain the points with sufficient precision. So, if you see 1, 2, 3, 4, 5, so up to 15 decimal places this has been obtained, and that is very important from a computational point of view, because we would like to do our computations in double precision, and if we want to do our computations in double precision, we should ensure that our these points, Gauss points or the integration points that we have and the corresponding weights are also obtained in double precision. So, very nicely all these points are given here. You see, for the 3 point rule we have these things and so on. Okay. So, here in this table I think the points have been given up to n equal to 10, up to the 10 point rule. So, 1, 2, 3, 4, 5. Okay. Yes. So, up to the 10 point rule, and in whatever we will do in this course and in most practical applications, you do not need more than a 10 point rule. So, now the question is, so given this 10 point rule, now you should be able to write a program where if I give you what is the n that I need, n specified, then you should return back to me the corresponding points psi I and the corresponding weights. Okay. Let us call this program or routine or a sub program, whatever you want to call it, as we will as routine or program, I will say program integ points, where the input is n and the output is the values of the psi i's and wi's. Okay. So, once we have this program where if I input the n, I should be able to output what are the coordinates of these integration points and the corresponding weights, then given this output I should be able to use this in the program. Now, remember, we are going to use this in our finite element computations, more importantly in the element stiffness matrix and in the element load vector calculations. So, we have to first specify what is n. Okay. This question has to be first answered in order to obtain the n, which will pass to this routine, and this routine will return to us back the coordinates of the points, integration points and the corresponding weights. So, how are we going to determine this n? So, let us first, to fix ideas, let us say that the objective of our program is to handle a material parameter which is linear at most. Okay. That is, it can correspond to a tapering bar. Okay. So, I can have this kind of a situation which I would like to handle, tapering bar. We will say that our distributed spring support or the elastic support is constant. We do not want this to be anything more than a constant. And when we say constant and linear, we mean that to be piecewise. That is, I could have this kind of a tapered bar, or I could have elastic support in only a particular region of my member. So, as long as it is satisfied piecewise, we are happy. So, Kx has to be piecewise constant. We are going to fix it, which is what our code is capable of handling, the finite element program that we are going to develop. Ea is linear, and this distributed load Fx, we will say it is at most quadratic. Okay. Again, quadratic, when we say, it need not be quadratic in the whole domain. It can be quadratic in one piece, 0 in the other piece, and linear in other piece, but not more than quadratic piecewise. So, if we have these things, then what is it that we have to do at the element level? So, if you remember, in the stiffness calculation at the element level, we had these integrals we had this thing into, we had 2 by h of the element d psi plus integral psi equal to -1 to 1 we had. So, if I am putting k to be constant, it will be k naught into, which is the constant value, ni hat nj hat into h of the element by 2 d psi. This is from what we have already developed. Okay. So, if I want to now fix the order of the integrands here, what are the integrands? This is an integrand, this is an integrand. Okay. If you look at the order of the first one, what is the order? The order of this one is 1, it is linear. The order of this one is p minus 1. The order of this one is p minus 1. Order of this one is 0. So, the total order of this integrand is equal to, for this one I will have order of the integrand is 2p minus 1. I simply sum up these orders. So, 1 plus p minus 1 is p and 2p minus 1. If I look at it here, this one is of order 0, this is of order p, this is of order p, this is of order 0. So, sum up the orders, this integrand is of order 2p. So, this order I will call it as p1 bar, this I will call it as p2 bar. Okay. Now, again let us look at, from the element k, what is my load vector. So, its load vector goes from -1 to +1, f hat function of psi ni hat into hk by 2 d psi. Again, by what we had done, this is of order at most 2, this is of order p, this guy is of order 0. So, this one, if I look at the order of the integrand here, the order is p3 bar, I will call it, is equal to p plus 2. So, for our integration rule, the order of the integration rule, to choose that, I will have to take the maximum of all these polynomial orders, because I would like to integrate the highest order polynomial exactly. So, what I will get is the order q is equal to max of 2p minus 1, 2p and p plus 2. Okay. So, you see that q is equal to, for p equal to 1, if I take this one is 1, this one is 2, this one is 3. So, 3 for p equal to 1. If I take p equal to 2, then this one is 3, this one is 4, this one is also 4. If I take p equal to 3, then this one is certainly less than this one, the second one is 6 and this one is 5. So, it is equal to 3 for the choice of the variation of the EA, F and K that we have chosen and the order of polynomials that we are picking for the approximation. So, the integration order, the maximum order of polynomial for which I would like to have exact integrals is governed by either 3 when p is equal to 1 or 2p when p is greater than or equal to 2. So, then our n is equal to q plus 1 by 2 will do the job when q is, this is true when q is odd. Okay, and this is equal to q plus 2 by 2 when q is even. So, you see that in our approximation a priori, even before doing our computations, we can fix what is the order of integration we need, because the polynomial order of approximation p, the material data, that is EA and K, and the load data are available to us a priori as input data. So, using those data I should be able to determine n. So, the next task is, if I know n, I know how to construct the integration points and the weights given the n. Okay. So, I pass this n to my routine intake points and it will output to me the integration points psi I and wi. Okay. So, once I have outputted these integration points, in order to do smart computations, remember that finally all this will be done by a computer, and the computer should not be subjected to repeated tasks over and over again. So, it is a good idea when I am using sufficiently large number of elements in the mesh, that then to construct the shape functions at the integration points. So, how do we do this? So, we can have another routine which we can call as shape all, which takes as input the P that we have and which outputs the following things, these arrays. I am giving it some names, PSI dot, TPSI dot, okay, where PSI dot can be a vector of size, can be an array of size the number of integration points into P plus 1, and DPSI dot is also of size n and P plus 1. what am I going to do here, that for each integration point psi I am going to load the value of the shape functions obtained, all the shape functions of order P obtained at this integration point. Similarly, here I am going to load at each integration point the values of the derivatives of the shape functions with respect to psi at this integration point. Okay. So, how do I do it? So, for you start loop over the integration points. Okay. For each integration point, you have already obtained or programmed the routine which will give you the shape functions at a given point. So, here I will put psi equal to psi I, which is the integration point, call shape function routine, to give n j at psi and dnj d psi at the point psi. Okay. Now, for j equal to 1 to p plus 1, I am going to do the following: psi dot I comma j is equal to nj at this point psi. Similarly, dpsi dot I comma j is equal to dnj d psi at this point psi. Then I can end the loops. Okay. So, this is a program which, or a routine again, which will take the integration points, the order of the shape functions that we want, which order shape functions. It will go to my shape function routine, return the values of the shape functions and the derivatives of the shape function with respect to the master coordinate at each of these integration points, and store it in an array where we have given it some name. The first array is the array of the shape functions psi dot, and the second one is the array of the derivatives dpsi dot. This, once we have loaded it, then you see that in all elements when we do the integration, then we do not need to call the shape function routine over and over again before we do the integration. We can simply use these two arrays that we have created, and these are not big, these are very small in size. Okay. We can simply use them and over and over again in each of the element calculation. So, in the next class or in the next lecture, we are going to extend this further. So, we have, if you remember, we have now developed capabilities to get the shape function at any given point, shape functions and the derivatives at any given point psi. Similarly, we can give you the integration points given the order of the rule n. And now thirdly, given the order p, we can get all values of shape functions at integration points. So, now we are going to use this information in the next lecture to obtain the suitable routine which can do the element stiffness matrix and the load vector calculations. So, once we have that routine, then we would have done a significant bulk of our 1D computational program, the finite element program that we want to write in one dimension. So, this we will start off with the next lecture. Thank you.